Welcome to Embedded Systems, lecture number 6. I'm going to continue on the notes, but I thought I would make the following observation comment. When you're in our field being embedded systems and really at the cutting edge of development of systems, you really need to keep up with what's going on in the world. Specifically with new tools that are available, new processors, etc. And so here is a good place to take a look at the current state of the art. For example, this is, if you just go to embedded.com, so if you just type embedded.com, you will get the EE Times, which is a publisher. You'll get their site, and there's all sorts of goodies on here. Here's an interesting one. How FPGAs, multi-core, and graphical programming are changing embedded design. It would be kind of nice to understand all of that. And unfortunately, I don't have enough time in this class to go into all that detail. I do cover this in a course like Advanced Embedded. So you'll need to take a look at some of the articles in here to be able to keep up, because things are changing all the time. For example, the homework assignment that you had to turn in last week, right? I asked you to look at an article that was how old? 8, 10 years, right? And then I said, contrast it with now. What's the differences? And so hopefully you got out of that when they said in the past that 8-bit microcontrollers were going to be the big behemoth and everybody would still be running with that, we're actually finding that a lot of people are going off to 16 and 32-bit because they're about the same cost as 8-bit now. And you get all the wonderful processing capability. Of course, what's the other problem associated with lots of processing capability? Lots of power, but also you get kind of lazy, right? It's just like the Windows bloat. When you get more memory, you create crap, or you create stuff that fills up that memory, and then suddenly your whole system starts to slow down. So there's the trade-off of you get better processing, but then you kind of fit your application with stuff that you may not need that. That's why in this class in particular, we pay a lot of attention to efficiency and Spartanism, in other words, try and keep things as basic as possible, because the more complexity you add, the more chance you have to fail, to have too much code, and run too fast. So I do recommend, and in fact in the future, for some of our homework assignments, I will put out more articles like this one. Microcontroller-based temperature sensors, accuracy considerations. And that looks like a neat article that I might want you to read this and then comment on it. In fact, this is an excellent article. I think I will have this actually assessed. So in one of your future homework assignments, I will say, go to this article and tell me about this. What's important about it? Because you got to keep reading. It's one thing you learn if you take some of our courses. If you want to be employed, you will continue to do education. All right? So let me get off my soapbox and start with today's discussion. So, as a recap, this is the application of a voice recorder. If you remember correctly, we were saying I have this voice recorder that, again, we're looking at linked lists, and maybe I should go up a little bit earlier and say if we're dynamically allocating memory, we're going to need to identify some space. And then the architecture that we have is when we record something, and it records and puts in a temporary buffer, you'll want to save that. And so you will malloc some space, you'll allocate some space, you'll copy all that data over, and it will exactly fill that space because you only need as much as there is. You will create a linked list structure, and using the concept of pointers, you will point to the top of this data that you will record, and then to the head of your list. In other words, this variable right here will say, I'm going to have a list of recordings, and here's the first one. And it points to this one right here. And this one will point to nothing because there's nothing else. But if you record something else, and maybe you put it again in this temporary space, you know how long it is. Again, you will malloc that space in memory that you have. You'll copy over the actual recorded message. You'll create another linked list structure. You will link it as the second one that you have in this whole list. You'll record something else. This time it'll be really long. You will, again, you will create some storage space that is identified for that single message. You will create a linked list structure associated with that, and you'll link it into your list. So that later, if you want to delete something, maybe the middle of 3 different messages, you'll say, okay, 1, 2, here's the second one. We will just free up this memory space, and I won't need it anymore. Then we have this right here, part of my linked list structure, which I will also get rid of because I don't need it anymore. And then I'll make sure to connect number 1 to number 3 since I got rid of number 2. So let's take a look at what our data structure is for our linked list of recordings. So you're going to have a linked list structure. In this case, this should be something that is familiar. Who's never seen a type def before? All right, we have 1 honest person. So I'm going to, okay, 2 honest people. Oh, boy, because you know what's going to happen. I'm going to give you a quiz, and I'm going to ask you to create a type def. So how many people have never seen a type def before? Oh, a heck of a lot more hands now. Okay. So again, the whole idea is that you are identifying a type. In this case, it's called a structure. The structure name is going to be list_t. And you're going to say, all right, this will consist of 3 in particular elements. Number 1 is an unsigned what? What does unsigned alone mean? Integer, right? So that means it's going to be 16 bits, and we want that unsigned because we're never going to have a negative size for a buffer, right? Our message will always have a size. It will never be negative 50 characters. Then we're going to have a char star. What does a char star mean? Right, it's a pointer. It is a pointer. The star is a pointer. It's pointing to a bunch of character data. But in this case, audio data is just going to be an address. So most likely it'll be a 32-bit address that will be associated with some data. And then, ooh, this almost looks recursive, right? Then we're going to have a struct list next. And what does this allow us to do? Literally, it allows you to do what we did here. Point to the next one. So it is just nothing more than a pointer, and the size of that pointer is just going to be to the next structure. And it's going to be called next. So let's say at a high level, we're going to have our temporary. Did this happen right? Ooh, sorry about that. Let's say we have a maximum buffer size, and again, when you do something with all capital letters, that means a constant. Typically, a style guide says that anything capital letters, you have a pound defined later. And that way we only have to define it once, and it's going to be some size. Then we're going to create a structure, And specifically, the recordings, or we're going to create two pointers. It will point to the recordings, and at this point it says no, because you don't know what it's going to be. You don't have any yet, actually. And then you have the current recording, because you don't have any yet, so you just set this pointer to be the value 0. You'll give it a address later. Every embedded systems loop, or every embedded system, will always have this inside of it. While 1. While 1 means do this forever. In this case, it's in the main, because an embedded system isn't like Microsoft Word or something like that, where you can exit, and then you're done and it's gone. No, an embedded system always runs and never stops. That camera back there that's recording this lecture will always be recording until you act, or will always be on and running until you hit that power button and turn it off. And so in this case, actually, even pushing the power button doesn't really turn off the power. It puts it in a special mode where it's kind of sleeping and taking only a little bit of energy. To really get that thing to power off, you would have to take out the battery. And then it would start out from scratch. So here's our system, and it will do the following. While those switches are pressed, which means what? It'll just stay in this one line, right? Until somebody presses a switch. Remember, this is our answering machine, or our recorder, I mean. So, if the button that we pressed was the record one, then we'll just run this little program called handle record. If we hit the play, then we'll do a play. Or we can go forward, or we can delete something. So obviously, we're not going backwards. We're just going to record, play, and we could advance to the next message. That seems easy enough, right? Is there anything in here that's difficult to understand? So simply, for our code for handling the forward, remember, we were saying that we have this structure in a linked list, as I said. So if we really looked at what this linked list is, I always wanted to do this. Wow, that's fun. Can I do that again? I've never taught with one of these. I'm sorry, it's just novel to me. So, all right. So we have this right here, and what is the name of that? It's called Cur recording, right? So it's a pointer, so it's a variable. Oops. Cur recording. And as it turns out, we kind of have a structure here, right? Oh, what's the other one? Oh, I got to get the previous slide. Recordings. I should be in there, right?
You are now.
Oh, it wasn't before?
No.
Oh. This is also a pointer. And to start out with, it's null. But eventually, what we're going to do is we're going to create some structures. So in this case, this will be 1, and it will have 3 elements. One is called what? Size, right? The other is called data. And the other is called next, right? Is it a capital N? I can't remember. Are any of these capital N's? Oh, I have it. Wow. Maybe I don't really like this. All right. But I'll have several of these. Now the interesting thing about these is that they're not given a variable name. It's just a block of memory. And how big is size? How many bytes? 2, right? Data is a pointer, which means it's how many bytes? It's an address, so we'll call it 4. And then next is what else? An address, right? So it's 4. So that means each one of these entities we're going to allocate 10 bytes for. The interesting thing is that in a linked list, figuratively, all we have to do is point over here to say, oh yeah, that's the next one, and oh yeah, that's the next one. When in fact it may actually be, this is memory location 04000000. This is X. All right. So what would be the beginning address of this one if we did it consecutively? 04000010, right? Because it's 10. 0A. And then this one would be 040000. 2 1
5.
It's 4. And if we did another one, 04000001D, right? Is that right? Yeah. E. So the contents of this one, if we're pointing to this one up here, is 040001 or 001E. This one points to 000, oops, 400014. This will be 004, oops, 400000A. Yeah, somebody told me that when you start writing in chalk, you do this. By the way, is this too small for you to see, or do I need to write bigger? It's okay back there? All right. At least you can read it. I know some faculty you won't be able to read it, right? So if I say, and so the, can you read that? So just for grins, if that is recording 1, recording 2, recording 3, recording 4, is there anything over there that I can fill? Variable cur reading or recordings? Or cur recording or recording? Is there either one of those I can fill? Raise your hand, because otherwise I don't know what you're saying. All right, go ahead. Current recording? Can we do that for sure? All right. You think that it's going to, what do I put there? First one? All right. When we first start all the way at the beginning, probably, yeah, we'll point to this one, which means this contents will be 04000000. What about recordings? Will that have anything in it? Probably same thing. Because we'll always want that to point to the beginning of our recordings. This one will change if we hit the forward button. We probably will say, all right, instead of looking at this one, the current one we're looking at is this one. By the way, don't forget, somewhere in memory, maybe in another big, huge block somewhere, starting at memory location 04100000, we have message 1. And maybe over here at 0400000001, 1, 1, 0, 0, 1, 0, we have message 2. And maybe this is 0, 4, 2, 0, 1, 0, 0, 0 is message 3. And I'll put message 4 over here at 0, 4, 2, F, 0, 0, 0, 0. I like zeros at the end. Plus there's another reason I might want to do this. Oh, by the way, which one? At the end, this is the last message. What do you think that's going to be right there? Nothing. No. And, okay.
Would it go back to the beginning?
Good question. Would it go back to the beginning? Do you need to know where the beginning starts? You already know where the beginning starts, right? That's in recordings. So you need to have some mechanism to say, no, you're at the end. And what's the mechanism to say you're at the end? Usually you put null in there. All right? So right now, turn to your neighbor and figure out the remaining values for these. You have all the data out there you need. You might need a calculator if you're not really adept at, you really don't need a calculator. I think you should be able to figure it out. So go ahead and figure it out. Can you pause it? By the way, for those of you who are watching this in TV land, yes, it was pointed out that there was a slight mistake since the increment of space here is a lot more than can be held in 2 bytes. So we changed this identification to a long word. So in this case, these are now 4 bytes. Because of that, this will now be C. This will be 8.
Yeah.
This will be 2, 4. Is this 2, 4 right here? Yes? Okay. So, who wants to give me their numbers for a trip to the prize closet?
For what?
How about our smart guys back there?
Sorry.
Who wants to give me a trip to the prize closet? Give me the numbers.
-3?
All right, what is this right here?
There's -3, right?
Zero, 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 1, 0, 0, 1, 0, right?
Yeah.
What's this?
No.
Oh, that address up there, right? All right. What about this one? Heck, would I do something like that? That was dumb. And then this one would be 0411. Right? 0411 0010. We're putting the message to, right? This up here is how much?
Do you understand what I'm saying? Yeah, and like you get that for calculators it comes with that.
And then
Just give you that. But the next one
042 0100. And again, this is roughly message 4.
tried it, probably not one.
042F. I just want to do this one first. And the size is 000. D or E? Who votes D? here who is thoroughly confused on what I just did. All right? And that is because why? What is inside of this? This is the element in the linked list called data. This, oh look, colored chalk. A little itty bitty scrap of colored chalk.
Little color unit, man.
I'm so excited. This is a pointer, and it is pointing to this. I got this to 0. So remember, data is a pointer, and it's pointing to the location of where the data is stored. That's where message 4 is stored. Here, what is this? Pointing to message 3. This is just pointing to message 2. This is just pointing to message 1. What a mess. All right. And oh, by the way, all you're doing here is pointing to the next one of these elements, the next linked list. This is going to be important because we're going to do later on when we're in the area of communications, RS-232 serial. We're going to actually do something similar to this. We're going to use an array. This is just the size of this. So in this case, the size is nothing more than 0411 0010 minus 0410 0000. So that obviously turns out to be 1000. Again, these are all hex numbers. So just to make sure that you understand, this is all hexadecimal. I just got lazy and didn't put the X in front of it. Do you think you could do something like that on a test? So is this a bit clearer? Mr. Morgan, you got it now?
Yeah, I just didn't understand the size aspect. That's
Okay. Well, I mean, that's reasonable. The size is literally how big is this, and it's nothing more than a subtraction.
The bottom on the next, those are the wrong numbers, right?
Oh, yeah, good point. Yeah, we fixed these, right?
Problem. Except for the 19 and the 24 and 26.
All right, so everybody would be able to get this if I gave it to you. Ooh, this is a nice quiz and test problem. I like this one. I'm going to do this one.
Awesome.
Pardon me? I'm going to do it exactly the same. Yeah?
I'm wanting to do that.
Yeah, that's the big trick. I'll probably give this as a quiz, and then I'll give it on the test, and I'll change the numbers all over, and I'll make it so subtle that you won't know. So if you're just copying your old notes rather than doing the problem itself. Yeah, by the way, how many of you already have files of what my previous tests look like? Yeah,
Now I don't got it.
oh, you know? Yeah, I have this habit of doing things like adding the word not in something, so that if you don't read it correctly, you kind of mess up. So make sure you read all the problems on the exam correctly. All right. This is valuable. You understand how this works. So now that I have, and keep in mind, this is the difference between an embedded systems engineer and a computer science person. A computer science would have absolutely no clue what's in here. And they wouldn't care. Because it's a pointer, and the system handles that. You as an embedded systems engineer may actually have to debug a system, and you're going to have to know where these things are. That's why embedded systems engineers get paid a lot more than those working in just computer science. You're in the right major. Woo! All right. Sorry out there in TV land, right? So, again, getting back into our recapping the structure. Everybody pretty much understands that. Oh, I didn't do this. It's called audio size, audio data, and next. Nobody mentioned that to me, right? Audio size, audio data, and that was So, since we don't want to type in all of these specific things all the time, what we'll do is we'll say, all right, using the assignment, notice that the pointer reference in the structure up there, the arrow. So what it says is, hey, if you're going to move forward, what you do is you take this address, right? And you look to see what the next one is, and you'll, in this case, if you go forward, no, you'll just take the next one, 040000C. So in other words, take whatever we're looking at, look at the pointer and next, and just overwrite the previous one and put it into the new one. So that's how you advance to the next. Again, the computer science world, we don't have to worry about that, or the software world, we don't have to worry about that unless you're debugging. The system handles all that. And oh yeah, if not current recording, meaning if it's null, right? So if it is null, that means you just replace what recordings is. In other words, you go back to the beginning. And that's how you handle the, reaching the end. So, this is where it gets interesting. So this is the example for the code that I want you to understand. Again, we're going to identify recording. So you're going to hit the record button, right? So the record button has been hit. I should probably go over there so everybody can hear me better and I don't shout my lecture. Because if I talk really loud, let's see, that doesn't turn out well, right? So, you've pressed the record button. And while you're holding the record button, you will continue to sample your audio. And this is a really simple function. All it says is I'm going to get data, keep getting data, more and more and more data. But what we have done is we've identified, in this case, unsigned car, new recorded means what? This is a pointer temporarily to the new recording that we have. So I'm going to record everything and put it in the buffer. Remember, it filled up the buffer. Finally, when we've gone to the end, this is unsigned I. This really isn't going to work unless, in our example, unless the unsigned long means it's going to be 32 bits. And so we'll have the size. Hey, that's one of the things that we need, right? Now what we need to do is we need to allocate this space over here. So, right over here, message 1, 2, 3, 4. That's what we're allocating the space that we're going to copy the buffer into. Then what we're going to do is we're going to copy our buffer into that new recording space. By the way, we call it here new recording. It's going to be an address. That's all we care about. Even though this is a function, the space is out there. As soon as we do this malloc, the space is out there. Oops. Then we will allocate enough memory for our structure. Then we're going to fill the structure. Specifically, we're going to put where the data is, where the audio recording data is. Boy, this is really fuzzy, isn't it? I'll have to fix that later. We're going to do the size. We already know what the size is right there. And then we don't know what the next element is. We'll just set it as null. But we do need something over here which says, okay, we have identified this data structure. We've identified this data structure right here, and we need to link it in to this right here. And so that's what that append will do for us. It will, in that append, it will just give us this address, and it'll put it in the previous one. Again, the delete, what we can do is we hit the delete button, and the main thing we're going to do right here is we're going to link the two structures together. We're going to drop out the middle after we've linked one to the next. In other words, we are linking this address will now be put here. So if at some point you change this to 0018, now you have just changed where this is linking to this one. You have this space, that's 12 bytes, and this is the second one. Let's say example, and you have all of this space that you need to do away with, and you free it. And so you use the free function to get rid of the data, and then the free function to get rid of those 12 bytes there that identify the structure, or that part of the structure. Now comes the difficulty associated with all of this. If you have oh man, I don't know how much I want to get into this. The operating system works such that it has a free list. In other words, it has identified where you have this memory that you can use for building these data structures. And I think it's going to be a little bit beyond this course to actually build that part of the operating system, where you say the free list points to the next amount of space that's available. Here it is. And oh, by the way, here's the next open space. And then you have the next open space. And then the next open space. So in other words, when you say free list, here, we have 412 bytes right here that you can use. And oh, by the way, here is some space right here you can use. And here is only 38 bytes, not much. And then here is only 88 bytes, not much. So we're going to assume that the operating system will do that for us. We won't worry about that until we get into advanced embedding. But take a look at that. What do you see? What's the problem with this memory allocation? I showed it really nice and pretty over here, right? Lots of space. What do you notice in this slide? What do you notice right here? Used. It's just pieces all over the place. And that's one of the problems with allocation of memory, is that you start splitting up your memory. And if you don't free it up, obviously you use it up. That's what we call a memory leak. when you don't free up memory after you're done with it, and there's nothing left. And usually you run into a problem that says, Windows comes up and says, I don't have enough memory, too bad, go away. Actually, the other problem is Windows doesn't say that. It just keeps on allocating memory even though you don't have it, it's paged, and makes your system run really slow, and eventually your whole system just dies, right? But in an embedded system, that's going to be really bad, right? Because eventually you have to give up. And usually that means that you reset or the system has to reset itself. We'll talk about that later when we get into Watchdog Commerce. And that's almost at the end of the semester. So when they're allocating, you have to continually allocating until you have no more free memory. There are also other types of facilities that you could use to actually squish up the memory. In other words, go back and figure out who's using what and try and put as much free space together. Again, the dangers of dynamic memory allocation. If you have a memory leak where you don't free it up, then you're going to waste memory and then not have it available when you need it. The other problem is that you may accidentally free memory that is being used, and then somebody else will use that memory space. The problem is when you start having the operating system allocate and free up, now you are taking a random amount of time or a varying amount of time of how much will be allocated and putting stuff in there. And if you have a real-time system, in other words, a system that must be hard real-time, it must respond within a certain amount of time, you might actually have some trouble during these garbage collection phases. And then, of course, the biggest problem, as I said, over time, you're going to fragment all this memory. But at this point, it's what we got, and it works for the most effect if you follow the rules, meaning when you allocate memory, you use it. When you're done, you free it up. So this is what's called a big pile of memory is called a heap that you allocate malloc free from that heap of memory. And every time that you repeatedly allocate and free, you're going to get differently sized allocations of fragmentation, which hopefully you have some operating system function that goes through and does what I called earlier the garbage collection. In other words, you're squishing all the free space together. So, one thing I want to talk about is an algorithm. Like that algorithm? That's one of the jokes I'm supposed to... Oh, come on. Everybody knows who Al Gore is, right? What did he do? What's his claim to fame? He invented the internet. That is correct, right? You know that's all a joke, right? It's the biggest running joke nowadays in communication. Al Gore did not invent the internet. I did. Not even close. The algorithm, no, the Al Gore internet, or for those of you who watch cartoons, I think they call it the Timmy, right? Anybody know the Timmy? Never mind. Look it up. An algorithm is I think I'm just going to ignore who invented the internet, by the way. An algorithm is a process or a recipe of how you will identify and write code, all right? So far we haven't written much code, but I think I need to talk a little bit about writing code and how you go about doing this. We actually have later discussion of writing algorithms, and I think I want to address a little bit of that now since I have 10 minutes left of lecture, and what better time to do it? So, to that, I'm going to go to the sheet of paper. Believe it or not, I am on notes page number 3, because as it turns out, notes number 1 is this, what it looks like beforehand. My notes 2 will be a copy of this, which I will then fill in all the answers. So this is number 3. So number 3, I'm going to talk about an algorithm and software design. If I tell you the following requirement that I want you to do, write software to take a temperature in Fahrenheit Is that close? Fahrenheit. And convert to Celsius. Is that right? Do I need a C?
Yes.
Oh, man. That's what I get for asking you young ladies up front. All right, I want to get a trip to the prize closet back from you. All right, here we go. Celsius. It was an S. How dare you? All right. So, if I ask you to write some code to do that, I should say, write software. I want a function. And the function will have an integer input, integer output. So, what's the first thing you do when you get this assignment? You immediately write code, right? You just sit down at a computer and write it, right?
Google. Pretty much.
You Google it. All right, assuming that you're doing it from scratch and that Google doesn't exist because Al Gore hasn't invented the internet yet. You have to do what? All right, the first thing you have to do is, as my math teacher once told me, sit on your pencil. Hopefully not in the wrong way, but sit on your pencil before you start writing and figure out what you want to do. So the first thing you look at this and you say, what is my process for software development? So the first thing you want to do is you want to, one, identify the requirements. Requirements are things like, what really does this have to do? That's one thing I haven't even addressed here. What's my range of numbers?
71 or 72.
Now I did say integer input, integer output, right? Well, I said integer input, integer output. Maybe accuracy, right? What else? What happens with errors? Right? If I'm out of range, what do I return with errors? So these are some of the things you identify the requirements up front. The next thing you do is you design. And usually in the case of design, it means we write an algorithm. An algorithm means we write it in words. We write it in pseudocode. This is not into C code immediately, but it's pseudocode, which is something similar. Maybe we do flowchart. And then the third thing we do is we code. We write the actual software. And then the fourth thing we do is, I heard it up there, test. And we test it by doing things like, we put in normal numbers. We put in abnormal numbers. That would be abnormal numbers, right? This is a reference to a movie. Look it up, right?
Oh wait, there.
We make sure we hit the normal range, but not every single number, and then we go just outside.
Bring that
Normal.
Yeah.
And of course, at the end, it's delivery. We deliver our software to whoever wanted it, and then we get paid, unless it's for a school assignment in which you get paid in a grade. How good or bad one? As I said, I'm going to go more into detail about all of these. In other words, what makes a requirement, and how you identify what the requirements of the system are. But you need to start thinking about this, because when you're given an assignment like Lab 2, which will be assigned soon, and will be due soon after that, you'll have to do some identification and algorithms to say, is this right? Is this how we do it? So what's important? All right? Any general questions before we call it a day? That being it, thank you very much.